Okay, sorry, something happened to my camera. So if we continue and do for tan, so we want to write the generic form for the whole angle tan theta plus theta, which is tan A. So for the generic angle, so for the generic form, which is given by equal tan equal to theta. So we have tan A, which is equal to tan theta plus theta, which is tan theta, is equal to tan theta plus. We're using this analog here to input our functions. So using that analog, we see that tan 2 theta is equal to tan A plus tan B, which is tan theta plus tan theta, which is 2 tan theta. Divided by 1 minus tan squared theta. Hopefully you can see that. So one thing we could do here is we could try as much as possible to solve for tan theta, which is going to be annoying to do because people be having. So if you cross multiply this, it's just going to be tedious, really. It's going to be confusing. But then we don't have to. We know that tan theta is equal to sine theta plus cosine theta. Okay, so we already know what sine theta is, and that's 1 minus that divided by that, and this. So the denominators will cancel out. So we have the numerator for this and the numerator for this, where the numerator for this will be the denominator for tan, and the numerator for this will be the numerator for tan. So tan of a half angle is equal to the square root 1 minus cosine 2 theta divided by cos 2 theta plus 1. Right, so I guess this actually gives you an analog of, gives you an idea. I keep saying analog. It gives you an idea of if you actually wanted to solve for this. Write everything here in terms of cosine. Leave this so you can have. Okay, leave this. Yeah, I think that's what you can do. You can leave this tan theta so you can actually solve for tan theta. Somewhere this 2 is going to have to disappear. And write tan squared theta if you wanted to do this on your own. So this is like a thing you can, if you wanted to practice it on your own. So you can write tan squared theta is equal to 1 minus cosine squared theta divided by cos what's happening? Squared theta. So write everything because the answer here is in terms of cosine. And if you write cos squared theta here, let me see what you can do. So yeah, you can actually. It's going to be long. I don't want to extend the video, but maybe I'll do it later. But this is the idea for the right everything, because this actually gives you an idea of how the answer, if you want to derive it. So this is like a circular proof. You can actually use this to prove this and prove for tan theta. So with this, somewhere these 2 is going to have to disappear. Write this in terms of cosine so you can have all your the things inside your square in terms of cosine as well. So yeah. So that's the idea. That's all for half and double angle identities. If you really wanted to see where the half angle is coming from, you should know that this is actually a half angle. You should know that this is a half angle. But then if you actually wanted to see the fraction, say, just use the same thing here. If x equal to half of x is half of x. Therefore, tan of half of x is equal to 1 minus cosine x divided by cos x plus 1, right? So it's really the same thing. Now, what are the should I say applications or implications? Well, there's nothing in mathematics. There's nothing in mathematics that's not somehow used in physics. If you want to, I'm gonna have to wipe out all of this so I can have space for. You know, deriving equations in physics is one thing. Understanding and doing physics is really another thing. I feel like anyone who knows mathematics, who understands, I don't want to say knows, who understands mathematics, can do the math in physics. So far as far as you understand the basics of math, you know how to do algebra, you know how to do, just like normal level math. I think understanding the math is easy, but understanding the physics is a whole other level. I wouldn't say, if I'm being honest, that I really, really understand physics to the highest extent. But the math, I can understand the math. I wouldn't lie to you, because it's just math anyways. As physicists like to say, it's just math. So my job here for the physics is just to show you the math. I don't think I'll be solving any questions on physics, because trust me, it'll take me like an hour to solve one question. So yeah, so for the physics, which is the application of trigonometry, we're going to do projectile motion. I'm going to use the whole board to derive today. Okay, where do I start from? Let's start from like the basic equations of motion in one dimension. So let's define our variables first. Let's define V as velocity after final velocity. Okay, and define V naught, initial velocity, A, acceleration, let's define, well, for one dimensional motion, let's define x, or delta x as distance. So, really, all the equations of motion, let's say V equal to V naught plus 80, V squared equal to V naught squared plus 2a x or delta x. What else? X of t is equal to V naught times t plus half at squared plus x naught. Well, if you're not too familiar with first order differential equations, you might be asking, what the hell is x naught doing there? Oh well, okay, for the sake of for the exercise, let me show you where the x naught comes from. The x naught is when t is equal to 0. So x naught is the initial distance. X naught. So we know the let's say x of t is equal to the integral naught. I have to show you why it's equal to the integral like this. So we know v of t is equal to distance or displacement divided by time, right? Or let me write in terms of calculus, is equal to dx dt. So dx is equal to v of t times ut. Take the differential to the other part of the equation because of integral. So x of t is equal to integral of v naught of t dt. Well, we know what v naught of t is. So we know what v of t is. So x of t is equal to integral, where is it, of this equation. So if you integrate that, so we have x of t is equal to v naught of t plus differentiate, integrate that, so you have half t squared times a, which is half a t squared plus an arbitrary constant c1. So t1 is going to be based on the initial value of t, or initial condition. So we say c1 is when t equal to 0. So x of 0 is equal to 0 plus 0 plus 0 plus c1 plus c1, so that's c1. So x of 0 is equal to initial distance, hence c1 is equal to x naught. So we can see that x of t is equal to this, but this is not necessary. Well, it's necessary for the sake of understanding where x naught comes from. But for also the sake of simplicity, we're going to assume that x naught equals 0. So we're going to assume that x naught equals to 0. Okay. So we are going to extend this idea of one-dimensional. Okay, so the thing about projectile motion is you can't really, if you think about it if you're not trying to cram or memorize facts and equations of projectile motion, because normally you hear that projectile motion is motion in 2D, and it is true, it's 2D, but can you ever have can you ever have a projectile that actually moves in a plane? Because for a projectile motion to be in 2D, it has to be the path, which is why the formula, the equation for trajectory of a projectile motion is a parabolic equation, but I think I'll derive that later on. Anyways, can you ever have a projectile that actually, I think it's possible, but it's hard to actually describe a projectile that actually moves on a plane, except if you're describing. It's hard, especially when it's in a field, like a gravitational field. But if it's on a plane, something like this, let's say this is on the ground, and you just threw something, you tossed it on it. This is a plane, so it traces a parabola. That'll be a case. But in a field, in any field, it's hard for you to say it travels in a plane or in a two-dimensional, path. So yeah, so sometimes you have to, well, for the sake of simplicity, to be honest, it has to be, let's just assume that it travels in a parabolic path. Well, it does travel in a parabolic path. It's going to be bent a little bit. Like if you threw something. Okay, so normally what we understand is, so this is the y-axis, so let's use the x-axis. This is y, z, x. So normally what you understand is if you threw something, it's going to go like this, like a parabola, yeah? But it's not really the case. Sometimes it might bend, so sometimes it could be parabolic, but it could be, let's say there is another imaginary line that goes like this, where if you're on the x-axis, it's kind of parallel to the x-axis. So it goes like this. So it's not really, it's like a twisted parabola like this. So normally the trace is supposed to go, so this is, normally the trace is supposed to go like this. You see what I'm talking about? Let me try more perfectly. So normally it's supposed to go like that on a plane, but it's possible that it goes like this. Okay, it's very possible. So this whole region is actually a three-dimensional region. There's a, well, I don't know, I really don't know how else to explain it, but hopefully you get the idea. But that's not what we're focusing on, we're doing two dimensions. Okay, I want to see where else I can go for this. Let's start doing the analogous equations for projectiles. So the acceleration will become gravity, and what I'm taking, what the description I'm taking is that if a body is moving against gravity, it's minus g, and if it's moving in the same direction as the force of gravity, which is a vector, it's plus g. So these are the main three equations to use. Well, there are like two other equations, but we hardly ever use them. So there is s x of t is equal to, is equal to v naught plus v divided by t times, divided by something times t. I don't know what the other something is, so v of t. Divided by 2. And really, this is how, from here, we can actually derive the whole, given that t is equal to change in acceleration on an movement. So we know delta A is equal to change in velocity divided by time, and so t is equal to delta v divided by delta a. And if you use this here, you can actually derive all of this equation, but that's not the point of today's, what I'm trying to derive today. So let me start with a graph. Not with a graph, but with a two-dimensional region. Okay, so that's a really deep problem, trust me, never gets better than that. Okay. You know, as I'm saying okay, I'm actually drafting out how I'm gonna actually write everything that I want to write. So I'm trying to give the best explanation as I can for projectile motion, because this is not just math where we are actually logically deriving from the, let's say, from basic axioms, but this is actually the application of math. Well, it's, to be honest, I feel it's not more stringent, but more deep in depth, because it's not just the math you're doing, but if I don't get to explain physics properly, the math is probably useless. So normally, when you throw a ball, you throw it with the initial velocity v naught, and it's given by, you throw it at an angle theta, but this angle is actually the angle between the x-axis and the tangential velocity. I have to draw a proper straight line like that. So it's not that straight, but it's a tangential velocity of the projectile you just projected into the air. So we say for the sake of simplicity that the whole thing is traveling in a plane, but you know it's not really like, as I said before, if this is the z-axis, it's probably going to land somewhere here. So the path is going to probably be something like this. And it starts coming here, here, and lands here. You see? So this is like an axis from here. So it's not really always in a plane. But for the sake of simplicity, we just assume that they're in a plane. Well, there are instances where it can be in a plane, but it rarely happens. But for the sake of neat mathematics, just neat and simple trigonometry, we're just going to say it's going to be traveling in a plane. Ooh, okay, so, okay. I'm a bit nervous, being honest, because I need to get everything right. So at a point P, at any point P, at any generic point P, where P is a variable, P is a point on the trajectory of the projectile. What is the trajectory? The trajectory is the path that the projectile travels. In this case, it happens to be a parabola, and I will show you later why it is a parabola. Well, it is a parabola, as you can see, but I will show you the equation that actually shows that it is a parabola. So at any generic point P, where P is a point of the path, where the path is the path in physics is the trajectory of the projectile, the body must have a horizontal component of velocity and a vertical component of velocity. Or there are different terms we use to describe the motion of a projectile, like maximum height, range, time taken, and so on and so forth. I'll get to that later. So at any generic point, P has vertical and horizontal component of velocity. But when it gets to the maximum height, which is somewhere here, the maximum, well, in the language of calculus, they say when the horizontal tangent equals 0. That's not quite in place. Let's move a little further. So when it gets here, Vy becomes 0, right? But the horizontal velocity never changes with time. And I will show you all of that, really. Okay, so can I draw? So because it's traveling in 2 dimensions, we do not just have x of t, we have x of t and y of t. So we see this whole, so the distance of the projectile to the ground is y of t, while the distance of the projectile, the horizontal distance, sorry, yeah, is x of t. So this is angle theta. Okay, so that's x of t, right? Okay, so I think I'm doing a good job explaining it. I'm not gonna lie. So let's start using analogs. What I mean by analogs is let's start writing equations that we can get from just this picture. So the first one is we don't just have velocity, because, well, you can have velocity for just one dimension, but now we have velocities in 2 dimensions. So I'm going to draw a line here. Okay, so this is where it's not even straight, right? Okay. So that's that for that. So now we start to do the things, what's it called? The equation. So v of x is equal to the initial velocity u. Well, we don't call, so we call the initial velocity v naught. So v of x doesn't change. So that'll be v naught cos of this angle because it's horizontal. So cos theta. While vy, so v of v, so this is the initial velocity. We're gonna write the what's it called? Because this, if this doesn't change, so for every point P, it's gonna be the same thing. So we're gonna call the vertical component of the, we're gonna call the vertical part of the velocity to be v of t, because that's the only thing that changes. So v of t, since it's projected at an angle, so it's going to be sine of that angle. So it'll follow this equation as analog, so it's going to be v naught sine of the angle theta minus gt, because, well, it's going to gain gravity, so it's going to be minus gt. Right, so yeah, that's that. Now we're trying to find x of t, which is the horizontal displacement, the horizontal distance traveled. So x of t, well, if you say velocity equals to distance divided by time, you see that distance equals to velocity times time, hence you say vx is equal to v naught cos theta times time, right? But if you use that same method here, you see it's not actually correct because you have to follow this analog here, this one. You have to have a half here, but you can't get the half. So you see that somehow we have to do an integral somewhere. You can't just define velocity to be distance. It is distance over time, but what else can I say, bro? I'm trying so hard to explain it. Okay. So velocity is equal to dx, or what am I using? So we're trying to find x of t, right? So is equal to integral of v of t or vx dt. Okay. So how do I know that? So I know velocity is equal to dx dt, right? So dx is equal to, we're doing for the horizontal displacement from there. So dx is equal to vx dt. So dx, x. So dx is known as the differential, it's known as the differential. So if you take the differential to the other part of the equation, it becomes an integral of vx dt. So x of t is equal to the integral of that with respect to t. Note, we are not differentiating the angle theta because it is constant, it does not change. So it will be v naught times t cosine theta. Okay? So that's the horizontal displacement, horizontal distance at any point, at any time t. Okay, so for y of t, we know that y of t is equal to the integral of v of t dt, right? So that's equal to integral of v naught sine theta minus dt dt, and that's equal to v naught t sine theta minus g minus half dt squared. Well, I'm actually omitting something here. This is actually going to be plus c1 here, okay? But C1, if you see, is the initial distance, and the initial distance starts at 0, 0, so that's equal to 0. But C1 here is actually equal to 0. So this is the equation for the y of t. Okay. So it doesn't go farther than this. Every other equation comes from these actually, but we know since this, because at any point it has a tangential velocity, so we say the velocity is a vector. Now we want to we want to know what the magnitude of the velocity at any point. It's not dependent on only the y component is dependent on time. So because we know magnitude of the vector is square root of, let's say if it's in 2 dimensions, the sum of the squares of the 2 vectors, and take the square root of the both of them. So for this case, we know what Vx squared is. Vx squared is equal to V naught squared sine squared, so cos squared theta. And V, now we have to actually do some algebra for V of t squared, or Vy squared. Let's call it Vy squared. So Vy squared is equal to V naught sine theta minus dt all squared, and that's equal to square minus that. So okay, yeah. V naught plus g squared t squared minus 2 V naught sine theta times gt. Okay. Okay, so that's Vy squared. So if you, let's write it like this. But wait, we can actually gt, let's how gt. Okay, we can actually do something. We can say Vy squared is equal to V naught squared sine squared theta plus gt, right? So we have, I want to see if I can actually, if I can actually get this from, so gt times gt minus 2 V naught sine theta. Let's see, V naught sine theta. Vt, wait, no, yeah, t is only factored out. So, gt, that. Anyways. Oh, okay, so look at something. Because, well, if we follow this analog, we see that, let's see if I can actually do the same thing. So, Vy squared, using this, is equal to V naught squared sine squared theta minus 2 g y of t. I hope you can see why. Why in this place the displacement or distance is y of t. Let's see. Can we actually? Oh, I guess we can actually do that. So from here we know Vy squared is equal to V naught squared sine squared theta. So if we factor out minus 2g out, so using this, so I'm using like a circular idea to prove it, minus 2g. So factor that out, so I have half g t squared, right? So half gt squared minus, okay, half g, sorry I'm being slow, so g squared, okay, minus v naught t sine theta, right? That's what I was trying to get before. There is a minus issue. There is a minus issue. I guess if I bring the minus out, I have is equal to v naught squared sine squared theta. If I bring the minus outside, I have plus 2g, right? Plus 2g. So this becomes positive. So you have v naught t sine theta minus half gt squared, right? And that's equal to v naught squared sine squared theta plus 2g. This is equal to this, y of t. Okay, so that's that for that. Let me look at my camera first. It's been a long time running projectile, so doing all these things actually brings the idea of what I used to do before. So it's been a while, so just forgive me if I'm being too slow. I've been looking at the board the whole time. Now I'm looking at the camera. Forgive me if I'm being too slow in recollection. Okay, so that's that for that. But if you are stubborn, which is good, actually, you might say, oh, but this is minus and this is plus. Well, it's because of the way I took it. Because, well, it's the same thing. This is g here. If it's positive, because I'm taking against gravity to be negative. So here, they're taking this as positive, so it can be plus g, really. It's actually plus g, but g will be negative, so it becomes minus, and here it's the same thing. So it's a more generic form for writing g. Okay. Whew. So now we're looking for the ideas we use to describe the motion of a projectile, such as time taken to reach maximum height and so on and so forth. So for v of t, which is the vertical component, equal to v naught sine theta minus gt, sine theta minus gt. We said at this point, at the highest point, the vertical component is 0. So at maximum height, at max height, let me see how much time I've exhausted. Ooh, longer than I expected. At max height, v of t equals 0. Hence, gt is equal to v naught sine theta. T is equal to v naught sine theta divided by g, which is the time taken to reach maximum height. Total time taken, t, or 2t, is equal to 2 times t. T is equal to 2 v naught sine theta divided by g. Okay, so that's what I'm taking. So what about maximum height? Maximum height. So where do you take maximum height from? Maximum height. Okay, so for maximum height, Vy squared will be equal to 0. So we know that Vy squared, let me draw a line here. So we know Vy squared, I'm going to change this positive to negative because equation